Hello, Mind Cities, grade 12s. It is your chance now. We're doing physical sciences. If you're joining us now, welcome, and tell all your friends that it is their chance to learn more with us and learn extra with us. My name is Abraham, and the name of the show is Learn Extra Live. I'm not alone. I'm with Phil. Phil, how are you?
I'm great, thanks, and you, Abraham?
I'm feeling so good. I'm about to learn more, and so are the Mind Cities at home. So it's reason enough for me to feel good.
Absolutely. Okay, well, I'm really excited about tonight's show. We're talking about the dual nature of light. Now, the thing that excites me about this is really new physics, so they should get their pens and pads, and specifically the notes online.
I like that one. And of course, Mind Cities, it is our National Science Week. What have you been doing?
Well, I've just been doing lots of science in the lab with my grade 12 learners, and we've been starting to take a look specifically into their final phase just before they go into prelims. So we're working hard in the science labs.
All right, I like that. If you haven't done anything, Mindset at home, it is your chance to do something. Here's your toolkit. All you need to do is to log on Facebook. Our Facebook page is facebook.com/learnextra. Like the page and join our 48,000 Mindsetters out there to help you also and for you to help them. Secondly, you can join us on Twitter. Follow us at Learn Extra. And lastly, you can download the notes for free that are proudly sponsored by Macmillan on learnextra.co.za/live. And the last thing that you need to know is that you can also ask your questions via our help desk, which is on the web page. The link is that it's mindset.co.za/help desk. It is in an easy format. You just go to that link and then ask any question, then we'll get back to you within 48 hours. But for now, Phil, take it away.
Thanks so much. Okay, well, Mindsetters, this is one of my favorite sections of physics. It's some of the newer physics. Most of the physics, all of that kinematics, all the mechanics and stuff like that, invented by Newton like over 300 years ago. Guys, this is the new stuff. This is the stuff which is at the cutting edge still. Now, this is one of the things which I find the hardest to understand, but the most interesting. Now, one of the things that really sort of sparks my interest is it's about one of my favorite parts of physics, and that's talking about light, and we're going to talk about electromagnetic radiation. Now, this is one of the more confusing things about light. I remember the first time a teacher told me in grade 10 that light was two things at the same time. All right, now this was the really weird thing, and we call this the dual nature of light. Now, let's just take apart the words. I'm going to do something a little bit strange. I'm actually going to draw all over the first slide without any information. Now, it says dual over here. Now, there's two things about light that I need to know. Light can both be a wave. Well, we know that from grade 10, is that light can be a wave. I know that it's a transverse wave on the magnetic and the electrostatic fields, and they're vibrating, and I've got all this lovely movement. I know what waves do. They bounce on things, they shine on things, and they get absorbed into things, all sorts of things. But now also, this is one of the really strange things. There were some observations about metal that led eventually up to Einstein winning a Nobel Prize that described light as a particle as well. Now you might start to think, okay, wait a minute. Okay, light as a particle and a wave. Does that mean that the particles vibrate like waves? No, guys. It all depends on the situation and how you observe the light. Now, it's kind of strange. I've got some lights shining on me here in the studio. It's kind of strange to think about them as particles. But it's absolutely true. Now, you might think, okay, well, if there's millions of these tiny little balls and they're striking Phil, how is he still standing? And if there's balls heading out of the TV and they're going to my eyes, how are my eyes still okay? Well, guys, now you've got to start to take a look at what sort of particles these are, and we'll get back to that. So now, let's just take it at the moment at face value that light can behave both like a wave and a particle. It just depends on the situation. Now, it's a lot like people as well. People can be both horrible and they can be really nice to you. It depends on how you treat them, and light is exactly the same way. People can behave in both ways depending on the environment and depending on how you treat them. And light is exactly the same. It depends on which experiment I use to treat light. Okay, so let's take a look at what we're going to be expecting in today's lesson now. Let's start taking a look at some of the words, some of the more difficult terms. Okay, guys, this is in the notes. Get the notes off the web so you're not like writing like crazy. You're actually listening to the show, watching us, and maybe even doing those experiments online with us. Those are coming up a little bit later on. Okay, so now the first thing which I see here is I need to describe EM radiation. Okay, now, wow, these are some words that I don't really understand. Okay, so let's just take this apart. EM radiation. Okay, well, the first part of that, I'm not actually sure what this means. EM stands for electromagnetic. Now, if you're watching over the next 2 weeks, you're going to learn exactly what the electromagnetic spectrum is. Now, EM radiation just talks about waves which are electric and magnetic in nature. You might say, okay, well, I don't have any electric or magnetic waves all around me. Absolutely, guys, you do. The only reason that you can see me right now is because of EM radiation. Let me give you some examples of what EM radiation is. The light which is shining on my face, the light coming from your TV. In fact, the waves which are going out from your cell phones, those radio and microwaves coming out from your cell phone are EM radiation. Now, this has led to a lot of speculation, a lot of problems, but we're going to discuss that in next week's lesson about this word radiation. A lot of people think that radiation is always a bad thing. Guys, without radiation, I couldn't see. I need light. Light is a form of radiation. Heat can be a form of radiation. Guys, don't be scared when you see this word, EM radiation. It just talks about the family of waves which are included together. And light is the one that I'm going to use as an example today. Okay, so now we've got to be able to describe these as both wave and particle. Okay, so just remember that it's just dependent on how I treat these things. So if I treat them as waves, they behave like waves. If I treat them like particles, they'll behave like particles, depending on the experiment. Okay, now the next two parts. I need to understand the conditions. It's just like those people, if you treat them nicely in a certain way, they'll behave a certain way. So it says I need to understand the conditions under which EM radiation behaves as a wave. Now, just on this point, I find this point particularly interesting, that it depends on how you treat them, they'll behave in a certain way. Now, if I expect light to behave in a certain way, usually it does. If you pick up a mirror, you expect light to reflect off it, and that is a wave property. Now, if you take a look at, let's say, for instance, light traveling through very thin fabric, what you'll notice is that the light spreads out. That's an example of a wave property. That's diffraction. In fact, there's many of these wave properties that light does. So we know that light does behave exactly as we would expect a wave to be. But now here comes the last piece. And this is the part that I find particularly interesting. It says, understand the conditions under which EM radiation, so that's all of those radio waves, microwaves, gamma rays, infrared, visible light, UV light, those are all EM radiation. This is when they become particles. Okay, now this is probably my favorite part of physics, especially in high school where I'm explaining the beginnings of quantum chemistry and quantum physics. Now, a lot of people use this word incorrectly and they use it to explain all sorts of really strange things. But over here, we're actually just talking about amounts of energy inside a particle. Guys, stay glued to the set. What we're going to be doing is we're going to be explaining this very carefully. Okay, so I know from reading through this list that today I'm going to learn about waves, and then I'm going to talk about those same waves, except they're like particles. Okay, now this is a little bit confusing. So what we're going to do is we're going to jump into their particular properties where I expect them to behave like a wave, then as a particle. There's two particular experiments that you guys can do. Now, if you've been following us very carefully, especially in the last hour with John, he used some simulations from a site called Fit. And what I'm actually going to ask is that during the break, we're actually going to post up links with this. Guys, I want you practicing this with us, and we're actually going to do the experiments with you guys. You can play around with the sliders, and you can toy around with this. And in fact, Fit has got some development in. From next year, I think they're actually going to let people play on smartphones and tablets, which is really cool.
That'll be so cool.
Okay, well, guys, like I said, let's start jumping into this. So the first point, okay, let's just separate out these parts that I know to be wave properties and then particle properties. Okay, so first of all, let's just decide what electromagnetic waves are. Now, electromagnetic waves are roughly similar. The only thing which changes is their wavelength. But now this is the really important part. All of them travel at exactly the same speed. And you might recognize the speed. If you look on your information sheet, this is the same speed for all electromagnetic waves. So that's for microwaves, radio waves, infrared, UV, visible, all of those. All travel at exactly the same speed. That speed is called c. Now sometimes on information sheets it's labeled as the speed of light in a vacuum. So when light or radio waves or microwaves are traveling through a vacuum, they travel at this speed. Now guys, this is incredibly fast. 3 times 10 to the 8 meters per second. Guys, that's 7.5 times around the world in 1 second. It's some pretty amazing stuff. These waves travel really, really fast. And I rely on this so that you can see what I'm saying and that you can hear what I'm saying. It's absolutely vital that you know that electromagnetic waves are all grouped together. They behave in a similar way. Now, I've just called them waves. So if I expect them to behave like waves, I expect them to do a few things. So if I decide to reflect them off a mirror or some sort of surface, I expect them to happen. I expect them to bounce off my incident ray, and then my reflected ray, and the angles should be equal. I will find that light does this very effectively. What about refraction? Absolutely. In grade 10, I was learning about refraction. That happens when a wave travels into a substance and it changes its direction because of that angle and the change in speed. Okay, so refraction is a wave property. Then the very last one. This is something that not a lot of people understand very well. Guys, especially if you haven't done 2D and 3D wavefronts, don't panic, guys. We're going to give you a brief intro. And for those of you that have already done it, we're going to rehash it and revise it quickly. And that is diffraction. Diffraction relies on something called Huygens principle. But if you're not too familiar with that term, or if you haven't done your studying yet for your prelims, you're not going to know what Huygens principle is. Not to worry, we're going to be explaining it using one of these animations. Okay, and then this is the part that I particularly like. So, electromagnetic radiation also behaves like a particle. Okay, now this is interesting. So, it also behaves like a particle. So, light can be seen as a stream of particles. Now, think inside your mind's eye about a stream of particles all moving together. This is kind of like hail shooting through space, or this is like particles moving through a river. Now, all that's happening is when light shines onto a surface, there's this hail of all of these particles striking the surface. And the way that I see these particles is when absorption takes place. Okay, now guys, this word absorption, you might have heard it before. Whenever my mom takes out a cloth and she wipes something wet inside the kitchen, it's soaking up inside that cloth. That's the liquid actually going up into the cloth. Now, absorption of light is when these tiny little particles of light are being taken into a surface. And you might say, okay, well, how am I meant to see this? How am I meant to see absorption taking place? Well, guys, if you're looking at anything with some sort of color, like this red shirt over here, the reason that this shirt is red is because of the particle nature of light. It's taking in the blue, and it's taking in the red and keeping it, but it's allowing the red particles back out. And that is something that absolutely blows my mind. When you start to take a look at absorption on a surface, you need to start taking a look at light as a particle. Now, if you've done the photoelectric effect, some of this might sound a little bit boring to you until we get to the really exciting part where we're actually using the photoelectric effect to explain light as a particle. Guys, there's a really cool experiment coming up for that. Okay, so sometimes it's better to use wave models and sometimes particle models. Now, you might meet with this word model a lot of times in science. That means that it's a concept or a way of explaining things. So sometimes I like to use wave descriptions for my particular electromagnetic radiation. But sometimes I rely on particle descriptions. It all depends on the circumstance. Okay, so when waves are being reflected, refracted, or diffracted, that means that light is behaving like a wave. But when we see light entering a surface, that's when it becomes a particle. When it gives away its energy to something else, it becomes a particle, and I need to think of it in that way. So what I'm going to do is I'm actually going to start with the next little bit. We're going to take a short ad break fairly soon, but I just want to start you thinking about what we're going to be doing inside FIT. Okay, so what we're going to do is we're going to take a look at an animation called wave interference. So let me just write that down for you. Okay, now wave interference, you might say, okay, well, where's the interference in terms of diffraction? Okay, we'll explain it as we go. So wave interference is where we're going to be doing our FET experiment, and this is going to show us how EM radiation, so electromagnetic radiation, actually behaves as a wave. So I want you guys to navigate your way around on the page, go download those notes, start sharing stuff on Facebook, and when we come back, we're going to start exploring EM radiation as a wave.
Thank you so much, Phil. Mindset is Remember, there are only 89 days left before you start your final examination, so there's just no time for you to just play around. All you need to do is just to work more and work extra. It's 89 days, 5 hours left, so you don't have any time. Also on the website, on our Facebook page, I've shared a link for the past exam papers. Get those past exam papers, practice with them, and see what the standard is, what the standard looks like. But otherwise, we're here to help you and give you a helping hand. See you after the break. Welcome back, matriculants. Now, over the Facebook page, I have a couple of comments that I'd like to urge you also, if you're having any questions, feel free to post them, and we'll get on them, and other Mindsetters will be there to help you. But Phil, before I give it to you, do you know that you have a nickname?
Do I? What
Yes,
is it?
From Reflector. Your nickname says, how on earth? Ne? And then it says, how on earth equal to make it simple. So make it simple. How on earth equal to make it simple with Phil. Nice one.
I'm very, very happy. Hopefully I am making this simple. Okay, well, guys, this stuff is the most amazing physics. And if you can explain it in a simple way to somebody else, that means that you actually understand what you're doing. So, guys, it's a really good test. If you've listened to our lesson, you kind of go, I've been listening to Mindset, and I know exactly what I'm talking about. Go and try and explain it to somebody else. The minute you start saying it's complicated, but it means that you don't actually understand, and you need to watch us a little bit more. Watch the reruns, watch the videos online, and start to try and figure this stuff out. Okay, well, before we went away on a break, I told you that we're going to be doing a little bit of an online experiment. Now, we're going to be taking a look at EM radiation. Now, just a reminder what EM radiation is. It's electromagnetic radiation, and in this experiment, we're going to choose visible light. So this is light which you and I can actually see. So it says it behaves like a wave when it's shone through a small slit. Okay, so we're going to do a bit of an experiment where we shine this particular color of blue light through a small slit and allow it to travel through. Now, something really interesting starts to happen when you put waves through a really tiny opening. They start to interfere with each other. Now, you might say, well, with each other, that sounds like there's two things. Well, actually, if you take a look at Huygens' principle, it says that what travels through there is not just a wave, but a collection of independent disturbances. Now, that might not make a lot of sense to you initially, but let's jump to the experiment. Let's see what it all looks like. Okay, so we're going to draw all over this. Okay, just a reminder which one we're doing. Guys, we're going to wave interference. There we go. Okay, so what I've got here is I've got a light source. Let's actually take away the graph at the bottom just to simplify things for you. I've got a light source on the left-hand side here. I've got waves which are traveling through a small slit. Now, what I'm going to be doing is I'm just going to draw a little bit on here, and we're going to try and see what's actually going on here. Okay, so what I'm going to do is let's just choose a nice color pen so you can actually see what I'm doing. I've got light waves which are radiating out in all directions. Unfortunately, that's a little bit blue, so let's make sure that you guys can actually see what I'm doing here. So there we go. Let's choose a red pen, and you guys, there we go. That's much better. So I've got waves which are headed out in all directions. Now, the waves that I'm interested in are the ones which are going directly through the opening over here. So those waves are the ones that I'm after. Now, what happens once they get through there is they start to make these circular patterns, these circular wave fronts. Now that, ladies and gentlemen, is diffraction. Diffraction happens when you've got all of these points which go through. Now, I'm just going to close the ink layer and let this go for a little bit. So let's just make the... There we go. All right. So diffraction happens when you send waves through a small opening inside here. Now, what that actually means, and I'm going to draw over this in a moment. There we go. What this means is that I've got these several particles which have now traveled through here. Now, you might be saying, okay, Phil, we're talking about waves. What are you talking about particles? Now, these particles are particles which are stationary. They are not the wave itself. Huygens' principle says that when a wave moves through an opening, that wavefront has got all of these particles. These particles act as independent sources for new waves. Now, without diving too much into the details, they each make their own set of waves which add up to a new set of waves. So what you've got as it comes out here is you've got these nice circular waves over there. Now, ladies and gents, interference has taken place. These small waves have added up in constructive interference to make these nice curved waves. Now you might notice that there's a graph on the right-hand side. If you're on the Facebook page, this picture is already over there. It's been fantastically posted up there, and we can actually start to see what happens on the screen over here. I start to notice that there are places where the intensity is much larger than I expect it to be. So I find that I've got these very large intensities in certain places, and you'll actually see it on the screen as very bright patches. So these bright patches over here are places where constructive interference is taking place. You can't interfere unless you're a wave. So this proves that light, when it's shone through a single slit over here, is behaving as a wave. It moves out in all directions like a wave. It diffracts as it moves through here as a wave. It even interferes with itself as a wave. So let me just explain what I mean in terms of the diffraction pattern. So if you're looking at the picture on the page, there's some really interesting pictures over there. So what I'm going to do is I'm going to trace out where the waves would have gone if no diffraction took place. So if no diffraction took place, all of the waves would land up nice and straight. But what I find is that some of them deviate. So if you're looking on the page, you've got this light band, dark band, light band, dark band. What I'm going to do is I'm going to trace the thickness of that central light band. That shows me that light has deviated. It has bent away from where it used to be. That means that diffraction has definitely taken place. Anytime light bends by going through a single slit, that means that it's behaved like a wave and it has diffracted. For those of you that have done 2D and 3D wavefronts, that means that Huygens' principle has taken place. And Huygens' principle definitely is talking about waves. Now let's see what we can change inside our program over here. So now we've got all of these things that we can change. We can change the wavelength, we can change the amplitude. Guys, again, these are terms which are associated with waves. So if I decide to change my amplitude, that means that my waves are getting less strong. So let's make sure that we've got all of that. I'm not drawing all over your screen there. There we go. So now I can change the slider to make the amplitude less. This is how you make the energy of a wave less. And you'll notice that everything on the screen gets lighter and lighter and lighter. That means that there's less energy moving out here. This is the way that waves move their energy, is through a large amplitude. Now you can go ahead and you can change your wavelength. You can do all sorts of things. I prefer to take off the barrier while I change the wavelength because it just makes the program work a little bit better. We can move up in wavelength and we can see how that changes your pattern. Guys, I encourage you to explore this program as fully as possible because it's got a really, really nice animation showing you exactly how the diffraction happens. So using this color, we can put back in the barrier and we can start to get our pattern. So you'll see the diffraction happening over there. Let's just turn up our amplitude so that you can see this very nicely. Nice dark lines is what we want to see. And then you can actually start to see the pattern occurring on that right-hand side. Guys, this is a really amazing experiment. It definitely shows you that light behaves like a wave inside the diffraction experiment. You can do it with 2 slits if you particularly like, and you'll get an even better experiment, and you'll actually see a more complex pattern happening on the other side. So guys, diffraction is definitely a property of a wave. Now you can actually see these really nice interference patterns taking place here. If we get a little bit of time next week, we're going to take a closer look at some of these other experiments that you can do. But guys, get playing around with this. Okay, now what we're going to do is we're going to jump back to that picture that I was talking about, and let's just say why this is light behaving as a particular wave. Okay, so there we go. That's our next experiment. Let's just make sure that we've got this all going inside there. All right. There we go. All right. So now on our diagram, what we can see is that light would have traced a straight path over here. It would have created a bright band in the middle there. I would have seen an area where there is brightness. So the waves have gone through there, shone on the screen, and made it really nice and bright. And that's what I'm seeing over here on this graph, that the waves are very intense there. But what I'm noticing is that there's areas where there's less intensity. And I'm just going to mark those in different colors. So these are dark bands. So you can actually see them on the screen there as slight darkening areas. That is the proof for destructive interference. So constructive interference, remember, was the yellow regions. Destructive interference was the areas of dark. So let's just move that down because I'm actually crossing out my own words there. So destructive interference happens when you've got things which are out of phase. And again, guys, these are definitely wave properties. Okay, So it says that light bends as it exits the slit, and that's why we get these really nice curved wavefronts. And I'm going to be drawing all over the picture. There we go. It's bending, and that's why I get that really nice curved wavefront as it exits. And this shows as light bands and dark bands. And that's because of the interference which is taking place. So constructive and destructive interference. Okay, but this is not the main event. We know that light is a wave because we've experienced light as a wave all of the time. Now, here's where I'm really interested in. Now, this is starting to talk about light as a particle. Okay, now guys, you might say, okay, well, Phil, how is it possible that light is a particle as well? Well, some things were starting to become apparent around about 150 years ago. Scientists started to notice that when you shine a particular type of light on a zinc plate, electrons start falling off the surface. Now, this was very, very, very strange. Now, they went and experimented and experimented and experimented, and what they found was that they couldn't use the wave properties to explain what was happening in front of them. This sat as an unsolved mystery for many years, and then along came Albert Einstein, 1905, this nice young chap with all sorts of ideas inside his head, and he wrote this amazing paper, which eventually won him the Nobel Prize. And that was dealing with the photoelectric effect. Now, he managed to say, okay, well, what if light is not behaving as a wave? He managed to say, okay, well, what if a particle of light lands on the surface? Now, you might say, okay, well, how do you start to think about light in a particle? Well, let's start out with the name of this particle that he suggested. Okay, so photons of light were these tiny little packets of energy. And he said that the way that light delivers its energy is more like little packets arriving at the surface than they are as waves. This would explain why one photon of light might give out one ejected photoelectron. Now, that's a lot of complicated terminology. Let's just slow it down for a second. Let's explain some of these words. Now, a photon is a little packet of light energy. That's the particle we're talking about. So this is a particle which comes and lands on the surface of the metal. Then, once that energy goes into the metal, it's able to spit out an electron. I call it a photoelectron. So this photoelectron is the electron which comes off the surface. So in comes the energy, out goes the electron. Now they might say, okay, well, a wave could kick out the electron as well. But now this photoelectric effect has really, really interested me for a very long time, and I'm going to show you why. It's because if the light energy isn't enough to kick out electrons, you cannot change the amplitude enough to get it to kick out electrons. You might say, okay, well, that doesn't make any sense to me, Phil. What does that actually mean? The way that light is arriving at the surface and giving away its energy is not in a steady stream like a wave would be, but it's in tiny, separate packets. And this is what Einstein was theorizing about. He said these separate packets had to have enough energy each, or the electron would not leave. Okay, so now he started to think about this, and he said, okay, well, when I'd start to do this experiment, we find that the energy on the surface is definitely delivered in these separate little packets. Now, the packets, when you talk about light, they're called photons. But in general, we can call them quanta. So photons are a type of quanta. Now, you might have heard of quantitative or anything to do with quantum. That just means how much. It's a tiny amount. So a quanta is just an amount of energy which was delivered to the surface. Now, here's why we explain it as proving the particle nature of light. We find that waves don't explain this absolutely. They say that waves transmit energy through their amplitude. Now, let's just talk about that first point. If a wave has a larger amplitude, there'll be more energy. So what we would expect is that if you just make the light bright enough, electrons would come off. But that didn't happen. So light was not delivering its energy as a wave. If the wavelength is too short, okay, now this is starting to get interesting. No electrons are emitted. So if the light was of too low an energy, it doesn't matter how bright it shone, no electrons are emitted, not even when the amplitude is increased. Now, what I'd like us to do is to actually go to Fit and actually start playing around with this animation. The Photoelectric Fit, this is one of my favorite ones as well. We've got a light beam over here. Now what I'm actually going to do is we're going to start playing around with all sorts of things inside here. I've got a really nice light over here. I'm actually going to draw all over it initially. So there we go. We've got a light beam. This light beam is going to shine on the surface of a metal. Now guys, I want you to play around with this. You can actually change the metal over here in this tick box. Okay, now what happens inside this experiment is the photon of light is going to go in and strike the surface of that metal. Now, if the photon has enough energy, an electron will make its way across this thing. This thing is called a vacuum tube. Now, the electron can make its way across the vacuum tube, and the electrons go around inside the circuit. Now, this thing over here is just a giant ammeter. All it's doing is it's measuring the current. Now, this is going to be useful in answering our exam question a little bit later. The current measures how much charge is going to be flowing. The battery down at the bottom, you can play around with it if you really want to, if you want to do a little bit of research. That's to provide what's known as stopping potential. Don't worry too much about it. But the whole idea here that we're going to investigate is this part of this experiment. Can the photon emit an electron? And how do we get it to emit an electron? Do we just make the light more intense, or do we change the energy of the actual particles? If we start to treat light like a particle, you'll actually see that this experiment goes well, and we can explain why electrons are coming off, but waves do not explain it. And we're going to prove it using this particular experiment. So guys, what we're going to do is I'm going to give you a little bit of time to surf on over to fet.colorado.edu and start playing around with this. Get onto this page and play with us.
Thank you so much, Phil. Mindsetters, don't go anywhere. Play around, but don't go anywhere. See you after the break. Welcome back, Matrix. Now, if you're still having some questions, feel free to visit our webpage for more help on our help desk. It is mindset.co.za/help desk. But for now, Phil, we have some questions that we have over our Facebook page.
Great, fire away.
Right, the first one is from Masilo Matapola. It says, what happens to those waves that do not pass through the opening?
Okay, those ones are going to strike the barrier. What happens when a wave strikes a barrier is it's going to bounce back. It's actually going to reflect off that wall.
All right, another one, it's from Bonginkosi Bongs. It says, what happened when the light get diffracted by the slit?
Okay, well, what's actually happening is as the light travels through that slit, Huygens' principle says that it's going to move out in all directions from there as well. So what's actually happening is it's going to change its shape to a nice curved shape. There's actually constructive and destructive interference taking place. That's called diffraction. So once you're diffracting light, that means that it's going to split out in all directions from that opening inside those barriers.
All right.
Hope that answers the question. If not, get onto the page and ask some more.
All right, here's a light one though. What did one ocean say to the other ocean?
I don't know.
Nothing. They just wave at each other.
I haven't heard that one before. Okay, well, as I said before the break, okay, guys, this is amazing. This absolutely blows my mind because the equipment to do the photoelectric effect properly is not that easily accessible. You can do it with an electroscope, but it's kind of difficult because you need a UV light. If we take a look at FET's done something really amazing for us. We've got a virtual lab over here. We can change intensity, we can change the wavelength, we can do all sorts of amazing things. Okay, now before I went away from the break, I told you to start taking a look at these targets. Now, what do I mean by these targets? Okay, quite literally what's actually happening over here is that I've got a target over here where the light ray is going to be shining on, and hopefully we're going to see some electrons coming out here. Okay, now let's first of all do the experiment incorrectly. Now, this is not something a science teacher usually says to me, but it's basically to figure out if this is a wave property. Okay, so now what I said to you before the break was, what happens if we shine a light and we start introducing more and more and more energy into this target? So in other words, if it's a wave, the thing which carries its energy is the intensity. So I've chosen over here, there's a little slider bar over here, there's some red light, we can actually change the color of the red light. Now this is nice low energy light, but what I can do to increase the energy of a wave is to increase its intensity. So the intensity is up at the top. At the moment, it's at 27%. Now, what I'm looking for is electrons which move their way across here. Now what you'll see is that as I start to move this slider bar, so let's actually see, it seems to be stuck. There we go. All right, so as I move the slider bar, let's actually move that with a pen. Oh, we're drawing on top of it. All right, we're a little bit stuck over there. We're fighting with Fit this evening. Okay, all right, now what actually starts to happen inside that intensity bar over there, as you move that across to 100%, as it moves across there, this 100%, that will increase the energy of the wave. Let's try and see if we can't get it right at the moment there. We got it right. There we go. We've got intensity which goes right up to 100%, and you can see that the intensity is as high as this can actually go. Okay, this proves that it's not delivering its energy as a wave. Because if I delivered with enough intensity, eventually I would start to see electrons coming off the plate. Okay, so now I know that it's not behaving as a wave would be expected to. Okay, but when I start to take a look at light as not as this really nice beam of waves, but as photons. Now you can actually do this. Inside the options of the photoelectric effect, you can say show photons. And I particularly like this. Now, photons are traveling these tiny little particles which are striking the plate. Now, this tells me that each one of those packets doesn't have enough energy. What you'll notice is that they're separate from each other, so the energy doesn't actually add up. So now, as we start to put these packets of energy onto my surface, if they had enough energy each, they would be able to free electrons. Okay, so what I'm going to do is I'm going to slow down the intensity. Now, when you start to talk about intensity in terms of photons, that just means less photons falling on the surface. Okay, now what I'm going to do is I'm going to give each photon more energy. And the way that you do that is by increasing the frequency or decreasing the wavelength. So, in other words, I'm going to change the wavelength to be a shorter and shorter and shorter wavelength. You can actually see the colors changing over there. So as the colors change, we start to get to higher and, oh, wait a minute, there we go. All of a sudden, I start to see electrons coming off the surface. When we reach a certain color in sort of the purple or violet region, I start to see electrons coming off that surface. And what you'll notice is that there is current down in that ammeter down at the bottom of the screen. So if each photon has enough energy, an electron will come across. And this is particularly important. We can actually start to see the current over here, and that is a result of me having these photons shining on there. Doesn't matter what the intensity is, I will still have some current. So you'll start to notice that as my intensity goes, there we go. So as the intensity goes up, all that happens is that the current will increase. It doesn't mean that it stops altogether. Now, the reason that the intensity increases the current is this, is that when I shine more photons, that means that there are more chances of electrons coming across. One photon, one electron. You might say, okay, well, there's a lot of photons shining on there. Where are all the electrons? I've got a little tick box over on the right here that says show only the highest energy electrons. I'm going to take that off and be prepared. What you'll start noticing is that there are tons of electrons heading across here now. Now we can actually see the full current taking place. So if you want to, you can take off the slower electrons. You can only see the highest energy electrons. But what I'm going to do is I'm going to take them off and I'm going to say, okay, wow, okay, there's all of the electrons. One photon, one electron. One photon, one photoelectron, which is taking place over here. The photoelectric effect demonstrates the particle nature of light. The wave nature of light did not explain what was going on here. If each one of those packets has enough energy, it'll free up an electron. If I take away each packet's energy, you'll start to notice that the electrons dry up. No matter what the intensity, my intensity is at 100%. That means that it can't be delivering its energy as a wave, which is continuous, which is dependent on my intensity. Okay, guys, please make it clear that this experiment is actually explaining the particle nature of light. Okay, so now let's get back to our presentation over here. Now here's the part which actually gets it. If the minimum frequency, guys, if you've studied this section already, you know what the name of this is. That is called the threshold frequency, and it's coming up in the exam question now. Any amplitude of light will release electrons. Okay, now this is particularly interesting. If the light was a wave, that would not be true. But because it's talking about each individual particle of light, this is true. The minimum frequency needs to be achieved. Now, the frequency is what decides the energy of my photon. And I told you that the energy of these photons can be calculated. Okay, so we're getting forward to an equation which looks a little bit like this. So the energy of a photon is dependent on two things: Planck's constant and the frequency of the waves that it's related to. Now, it's not the frequency of the photon. A photon is a particle. It's the frequency of the wave that it relates to. Its dual partner. Okay, now we're going to start using these. Guys, we're going to jump into the exam questions. They're two particularly nice ones. You might actually notice these are actually from the end of your papers last year. So guys, please make sure that you actually understand what's going on here. They are from the end of your paper. You might even recognize the apparatus on the screen because we've just done this experiment. So it says the diagram below shows light incident on the cathode. And you might say, okay, well, cathode's something that sounds a little bit scary. Cathode sounds like redox. Okay, cathode is just where reduction, or at least the gaining of electrons takes place of a photocell. So the ammeter registers a reading. Okay, so now that means when it registers a reading, that means that electrons are moving, guys, because ammeters tell me that there is current flowing. That tells me that I've got current which starts to flow throughout my circuit over here. Okay, well, that's quite interesting. That means that my electrons are being freed up from the surface and being shot out into space and completing the circuit and allowing this ammeter over here to have some sort of current. Okay, now there's a couple of options here which we need to consider before we answer this question very carefully. Now, it says which one. Okay, now that means that there's only one correct option here. So it says which one of the following correctly describes the relationship between the intensity of the incident light and the ammeter reading. Okay, well, guys, this means we can just go back to our PhET lab. Let's go back to the photoelectric effect, and let's get those photons emitting some light over there. There we go. So there's our photons emitting some electrodes. There's some current. We've got exactly the same experiment as those inside my multiple choice question. Okay, so now what is the effect of intensity on current? So let's go down to a low intensity. Let's make sure that we start out with a very low intensity. So I've got a very tiny intensity. You'll notice that the current is very, very low. What starts to happen when my intensity increases? So let's just take that away. Let's move. There we go. I've increased my intensity. I've started to get some current. Let's move my intensity a little bit further up. You start to notice the current increases anymore. Okay. Now, guys, when you start to take a look at the photoelectric effect, intensity actually just talks about the number of photons which are striking on that target. So the greater the intensity, the more photons there are, the more electrons there are, and therefore the more current will flow. So let's max it out. Let's make sure that my intensity goes right up, and I can see that my current is climbing very nicely because there's more electrons which are flowing through my circuit. Okay, so more photons, more electrons, more current, and that seems to be a very nice answer. So let's try and find our correct answer. We've already got a correct answer in mind. Okay, so we looked at intensity. Just a reminder that when we talk about intensity, all right, and we're talking about particle nature of light, intensity is related to the number of photons. Okay, so now let's take a look at our options and let's try and weigh up which one is the best. So as intensity increases, the ammeter reading increases. That seems around about right, because the ammeter reading is talking about photoelectrons. Photoelectrons are the thing which give the ammeter reading. So photoelectrons are the thing which make up the current inside that experiment. Let's look at our other options and let's see if there's anything else which makes sense. Okay, so as our intensity increases over there, all right, our intensity increases, the ammeter reading remains. Oh, no, wait a minute. It doesn't remain the same. Guys, we saw it changing. As the ammeter reading decreases, that was due to an increase in intensity. Guys, that doesn't make any sense either. What about the last one? As I decrease intensity, we only did that once, the ammeter reading somehow increases. Guys, that's incorrect. So the only possible answer here is that as my intensity increases, my ammeter would also go up. And that's because there's more photons. More photons means more photoelectrons. Very nice example of how those two are related. In fact, they're directly proportional to each other. Okay, so guys, we're going to move on to one last question. I think we've got about 8 or 9 minutes, so let's just try and make sure that we fit this in very tightly. Okay, now I particularly like this one as well because it's another photoelectric effect. You can see I like these questions. So it says, during an investigation, light of different frequencies. Okay, now different frequencies means different energy. Is shone onto the metal cathode of a photocell. The kinetic energy of the emitted photoelectrons is measured. So I'm trying to figure out what's going on with the kinetic energy of electrons which come off here. The graph below shows the results obtained. Okay, so now let's look at this graph. I hope it's nice and big on your screen and you can actually see what's going on. This is a kinetic energy of my electrons. At the bottom here, I've got frequencies that I went through. In other words, that's the different colors that I went through. Now what you'll notice is that I increase my frequency, but electrons are not budging. They're not moving at all. Now they don't even tell you what intensity this is. That tells me that we're dealing with the particle nature of light. Once again, the photoelectric effect. Okay, so let's look at some of the questions that they ask us. So it says, for this investigation, write down the dependent variable. Okay, so a dependent variable. Guys, I hope you were watching the grade 11 show. What a dependent variable is, it's the one which I can measure as a result of something else. Now, what I can tell you is that you cannot go down to a microscopic level and start adjusting your electrons' kinetic energy. You don't have a spanner that tiny, you can't tell the electrons what to do. Guys, this is something which I measure. There's also another giveaway. The fact that it's actually drawn on my vertical or y-axis is usually a sign that this is my dependent variable. That's usually where you put the dependent variable. Now just to check, let's check what the independent variable is. Now, how do I tell an independent variable? Well, the way that I remember this is because it starts with the letter I. It's the thing which I change. I can change the frequency of the light. The way that I can do that is by shining different frequencies or different colors onto the surface. I increased the frequency and then measured the kinetic energy of my electrons. So my independent variable over here, so there we go, my independent is definitely my frequency, because that's the thing which I can change, and independent also starts with an I. Independent, I can change this. So I changed my frequency and I watched for the kinetic energy of these particles. Then, the most important parts, the controlled variables. Okay, now I've got to be a little bit more careful. Right, so it says, during an investigation, light of different frequencies is shone onto the metal. Okay. Which metal I used during my experiment cannot change. My metal is definitely something which can change the outcome of these experiments. If we go back to our photoelectric effect, we'll start noticing something particularly interesting. You can actually change how much energy these electrons have got dependent on which metal I use. You might notice that these electrons are moving at a certain speed. What would happen, for instance, if I replaced that with copper? Wait a minute. If I change it to copper, there's not enough energy to get them off there, and I've actually changed my experiments. So the metal itself is a controlled variable. So that's not really fair. You can't go swapping out the metals when you're starting to do a fair test of my frequency and my kinetic energy together. So one of the controlled variables over here is the metal. Okay, so I'm actually going to write that down because a lot of people wouldn't have spotted that, but it was described in the wording of the equation. Now, something else which you need to keep constant the whole way through your experiments is your intensity, because it's not really fair that you start changing the energy of something else. It might affect your results. So metal is the most important one because that will change your results. Intensity shouldn't. Now, I want to start taking a look at some of these things which are going to extend into next week's lesson. This word threshold frequency. What is a threshold, guys? A threshold is a minimum. It's a barrier. It's something which I need to get over. Now, if I start taking a look at a threshold frequency, you start to notice something on the graph here. My graph draws a really nice straight line, but only from around about here. You notice that my graph only starts from a certain frequency, and that's around about 8 times 10 to the 14 hertz. Now you might say, okay, well, why does it only start emitting at around about there? Okay, well, this is the threshold frequency. Guys, if I start to take a look at this, this is the minimum frequency that it requires to emit electrons. Below that, there's no kinetic energy. Guys, take a look here. That is zero kinetic energy. The electrons are not moving. That means that they have no kinetic energy. I have not met the minimum requirements for frequency. So there it is, my threshold frequency. Let's line that up nicely and get an accurate reading off there. So I see, okay, there we go. We got all the way through to, and I think inside there it was saying 8.5 or around about 8 times 10 to the 14, and this is what they're asking us to do in the next one. So it says use the graph. So I'm using the numbers off the graph to obtain the threshold frequency. Guys, the threshold frequency has got a particular symbol. It's F0. That means F standard. And that is equal to, let's call it 8.5 times 10 to the 14 hertz. That's the minimum frequency that it requires to emit electrons. Okay, but I'm going to stop here for a second and just explain something. A lot of you are saying, okay, well, Phil, you're talking about frequency a lot. I thought you were talking about particles. Guys, this is talking about the frequency at the energy where I can free electrons off. Now, this is related to the other energy is equal to HF. Remember this equation? This is the equation that I gave you just now. That is the energy of one single photon. Now we're talking about particles again. So it's the energy of one photon. But now this particular energy has got a very, very specific name. This is the amount of energy when you actually manage to pull an electron off there. This is the energy of one photon. I'd like to explain something further, but are there any questions before we finish up?
Yes, I do have some questions.
Let's fire off a couple of quick ones.
Here's
We've got a minute
the
or
first
two.
one from Sovo. It says, what do we call a point where constructive and contractive wave meet?
Oh, constructive? Okay, I'm with you.
Yeah, and even a point where constructive and destructive waves meet each other.
Oh, okay. What he's talking about are nodal and antinodal points. Okay, so now let me just talk to you about this. So when you've got constructive interference, meaning that you've got two waves of the same type, so two crests, two troughs meeting in the same points, that's constructive interference. What you're looking at is an antinodal point. Where there's destructive interference, that's called a nodal point, and that'll be a dark line. I hope that answers that question. We've got time for one quick more.
All right, from Gentle, it says, why the emitted electrons have a range of kinetic energies up to a maximum level?
Oh, okay. Okay, right, really excellent question. Basically what I did was I selected for only the maximum one. Now the equation, the photoelectric equation, only describes the maximum ones. Some of those electrons have to fight their way through other energy levels to get off the atoms, so they're going to have slightly less. Unfortunately, we're running out of time.
Yeah.
I love this stuff, but we've got to stop.
Next week, it's going to be another one.
To be continued.
All right, Mindsetters, let me take also this time to remind you that we have a new show, a talk show, which is called Connections, which you can catch tomorrow from 7:15 up until 8 o'clock. We're talking about social health, and the topic is drugs and alcohol. Don't miss it. Like the page also on Facebook. But from us, we just want to say we appreciate you taking your time and learning more with us. All the best as you prepare for your exams. And my last words, as I always say these words, never ever stop believing in yourself, because when you stop believing in yourself, no one will ever believe you. The whole world will never believe in you. But from us, cheers, peace, we love you.